10.6 power series. So power series with center C is an infinite series given as capital F is equal to the summation from 0 to infinity, a sub n times the x minus c to the n power. So that's going to be a big focus throughout this section. And it obviously could be written out with each of the terms as shown there. So x is a variable, okay? So we have the n going from 0 to infinity, and then x is some variable. So for example, the f of x given there in equation 1 shows it as 1 plus x minus 2 plus 2 times x minus 2 squared, etc. So that has a power series with a center of 2. So just giving a little bit of context to what a power series would look like. The second page is a ton of writing, also straight from the textbook. The focus is about where does it converge absolutely and where does it diverge. So if the absolute value...
Mr. Rodriguez?
Yes.
Sorry for interrupting.
Yep.
But it's quite blurry.
No problem. I don't know how much I can improve that sign. It's all on... We could try turning off the lights. Go for it, Nico.
Thank you, Nico.
Is that any better? It is on
That's a bit better.
Okay,
but
it's on Canvas.
You zoom in a bit on it, which worked last time with like the camera. I don't know. No, it looks good. It looks good.
I'm sorry. Yeah. It is on Canvas if you want to pull up the outline version of the notes, or this is straight from the textbook. Things that you need in the yellow there, f of x converges absolutely if the absolute value of x minus c is less than r, and r is going to be known as the radius of convergence. And it diverges if that absolute value is greater than r. So we will essentially be looking for this interval of convergence. And it can be an open or it can be a closed interval. And then this graph is just, showing exactly what I said, where in between, when it's smaller than r, then we are converging absolutely. When it's larger than r, it diverges, and we can have possible convergence at those endpoints. So hard to move this. It's a theorem, not so much that we're totally pulling from it, more just understanding from it. So radius of convergence, this power series has this radius of convergence r. It's either a non-negative number or infinity. And if r is finite, then it converges absolutely when that absolute value is less than r, and it diverges when it's greater than r. And if r is infinity, then f of x converges absolutely for all x values. Okay, it's saying that there's no bound on when we converge.
Will we find the r value?
Yes. Yes, we will find it. So we will be using some of the tests that we've seen in previous sections, specifically the ratio test we'll use a couple of times here, and that will help us figure out what that r is and then move from there. Okay. Good to move on to the first example, or are we still copying?
About 20 more seconds.
No problem. All right, here we go. So example 1, using the ratio test, where does capital F of x, this power series, x sub x to the n power over 2 to the n power, where does it converge? So we're going to first find that radius of convergence. So I'll label this as kind of our step one. And we're allowed to use that ratio test, or that will be helpful, because then we can remember if the ratio ends up being less than 1 when you do that limit, then you have something that converges. So that will allow us to do this comparison of kind of when is this simplified limit less than 1 to be able to figure out that radius. That's our goal right now. So we're saying that our a sub n is x to the n power over 2 to the n power. And then we're looking for the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. So we're going to fill in our a sub n plus 1, which would be x to the n plus 1 over 2 to the n plus 1. And if we divide it by a to the n, then we're multiplying by the reciprocal. So we would be multiplying by 2 to the n over x to the n. And we can simplify a lot here. The x to the n's and the x to the n plus 1's cross cancel to just an x to the first. And same with the 2 to the n's, leaving us with an 2 to the first. So this really reduces to the limit as x approaches infinity of 1/2 absolute value of x. And that 1/2 could be put in front of the limit as well. So we are saying then, right, there's no n's left, so there's nothing to really evaluate in terms of the limit. So this is equal to 1/2 absolute value of x. And based on our ratio test, if that limit is less than 1, then we have convergence. So in this case, when is 1/2 absolute value of x less than 1? When the absolute value of x is less than 2. So therefore, f of x converges if absolute value of x is less than 2, making our radius of convergence r2. So we sort of have this open interval right now from -2 to +2 that could work. Right? The center is 0 because I don't have x minus some constant. So from -2 to 2 is really our open interval, and we want to check those endpoints. Do we converge at -2? Do we converge at +2? So that would be step 2. So we want to know what is f of -2, what is f of +2, in terms of do they converge, do they diverge. So if I'm evaluating f of -2 first, then I'm looking at the summation. Infinity, -2 to the n power over 2 to the n power, which is alternating. It's 1 minus 1 plus 1 ... So this is one that diverges, right? It doesn't end up going to some value. It alternates back and forth. And then f of 2 from 0 to infinity of 2 to the n power over 2 to the n power. I wrote that backwards. Well, that's just equal to 1. So it's just going to constantly add 1s, which also diverges. Okay, so therefore keeping it as this open interval is accurate. We wouldn't close off at -2 or 2. Both of those diverge, so it converges in between -2 and 2. So f of x converges here. right, so example 2, it's going to be similar. We're going to approach it again with the ratio test. So now f of x is defined as, from 1 to infinity, negative 1 to the n power over 4 to the n times n. So that's like your a sub n times x minus 5 to the n power. There's your power series. Okay? So definitely more complicated here. But we're going to actually approach it in the same way. So a sub n, we're going to name for the ratio test the whole thing. When I said a sub n before, that just meant in terms of the power series definition, it had an a sub n in the front and then that power part. But when I'm doing ratio test, the whole thing is my a sub n. So let me just define that for us. Okay, so again, we're looking for that limit as n approaches infinity, absolute value of a sub n plus 1 divided by a sub n. And we want to know, when is this less than 1? So the limit as n approaches infinity, the a sub n plus 1. We can drop the negative 1 to the n power, right, because we're looking at the absolute value. That's just what's making it alternate. And everything else is going to come through. So I would have an x minus 5 to the n plus 1 divided by 4 to the n plus 1 times n plus 1, multiplying by the reciprocal of a sub n. So I would have a 4 to the n, an n, x minus 5 to the n. All right, and then we're going to take a look at how do things cancel, but not everything does this time around. So the x minus 5 to the n and the 4 to the n, they both cancel. I'll change colors to show that a little more clearly. So this is gone, and 4 to the first is left. And then this is gone, and x minus 5 to the first is left. So I'm left with the limit as n approaches infinity of x minus 5 times an n over 4 times n plus 1. Okay. So I really am looking at the n terms, right, when I'm doing my limit. So I can pull that x minus 5 out, and that's the portion that needs to remain in the absolute value. The n's are all going to infinity, so they're already going to be positive. We don't need to worry about keeping it for that portion. So now I have n over 4n plus 4. Well, the limit of n over 4n plus 4 as n goes to infinity is just a fourth. The degrees are the same. So this is going to be equal to 1/4 times the absolute value of x minus 5. All right, and my job is to figure out when is this less than 1, because that would be my radius of convergence. Greater than 1, it diverges. So then x, absolute value of x minus 5 is less than 4. Makes that limit less than 1. So in this case, right, I have my r equaling to 4. My center is equal to 5. So then if you think about, I mean, just kind of visualize a circle, right? If your center's at 5 and you're allowed to go 4 in every direction, if we just stick with the x and the little x's, that would be a lot easier to think about. But then we can go from 1 to 9, right? So that's the interval we're thinking about right now. Now our job is just to figure out, is it inclusive of either 1 or 9? It could be one or the other, neither, both, but we need to check them. Just to see, am I turning this into a bracket at all? Or does it remain open? But right now I know that it converges definitely between there. So I need to know when x equals 9, I need f of 9 would give me negative 1n over 4 to the n 9 minus 5 to the n. Well, 9 minus 5, using my center here, is 4. So then I really just have a 4 to the n twice, and I can cancel those ones out. Okay, so then I end up having negative 1 to the n power over n is my series. And if I went back and looked at my Leibniz test, oops, what did I do? There we go. This one converges by Leibniz test. Okay. And then I would do the same thing at 1. So since it converges, I can turn the parenthesis next to the 9 into a bracket. And now I want to take a look at what about 1. So for the 1, I have negative 1 to negative 1 to the n power, 4 to the n, and I have a 1 minus 5 to the n. So now, when I simplify this, 1 minus 5 would give me a negative 4 to the n, which is going to cancel out my negative 1 to the n, because it will make it positive, and my 4 to the n. So all of that's gone. So I am left with 1 over n, which is a harmonic series, and this diverges. Okay, so therefore a parenthesis is good, and my conclusion would be that it converges 1 to 9 inclusive of 9. Okay, so example 3 has an even power series. So where does this one, where it's x to the 2n power over 2n factorial, where does it converge? So again, using our ratio, we have to be a little bit creative here. Remember when we first saw the factorials, I forget which section it was, we looked at the n plus 1 factorial as n plus 1 times n factorial so that we could cancel things out. We're going to do something really similar here so that we can cancel things out as we need to. Okay, so a sub n, first of all, is defined as the x to the 2n over 2n factorial so that we can do our ratio test again. And I'm going to write out a sub n plus 1 right now so we can see exactly how we are going to treat this. So the first thing I'm going to do is x to the 2n, but having n plus 1 in there is 2 quantity n plus 1. So it's going to go to a 2n plus 2. And same idea with the factorial. It's 2 n plus 1 factorial, or a 2n plus 2 factorial. Okay, so then before I continued, I did a little side work and I said, well, 2n plus 2 factorial is equal to two n plus 2 times 2n plus 1 times 2n factorial. Right, so I was able to break it apart so that I'll be able to cancel that 2n factorial later on that I need to. But there are two factors prior to, or not prior to, after the 2n factorial portion. Okay. All right, so now when I go to my ratio test, I have x to the 2n divided by 2n factorial multiplied by the reciprocal. So 2n plus 2 factorial, which is equivalent to, oh, I'm sorry, I wrote it in the wrong order, didn't I? Let me go back. Okay, so this should be x to the 2n plus 2 divided by 2n plus 2 times 2n plus 1 times 2n factorial, now multiplied by the reciprocal, where 2n factorial is here, over x to the 2n. Okay. So now as things cancel out, we do have our x to the 2n canceling, leaving us with an x squared. And we do have our 2n factorial canceling, leaving us with 2n plus 2 times 2n plus 1. So we have absolute value of x squared over 2n plus 2 times 2n plus 1. Okay. All right, so from here I can pull out that x squared and just look at the limit of the n terms, which the denominator is obviously the larger degree, so that limit zeroes out. So we would have the absolute value of x squared times 0, which is equal to 0, which is always less than 1. And therefore, we can make an always statement on this one that it will always converge, implying that the radius of convergence is infinity. So we don't have to test endpoints on this example. Okay, so a quick summary of the problem that we just covered. This is bringing back the idea of geometric series to power series, specifically where our radius, or our r, is less than 1. So with those geometric series, when the r was less than 1, we were able to use the formula of 1 over 1 minus r. So now we can combine this with the idea of power series and say that this is true if our radius of convergence is 1. So all we're doing in this example is proving that something similar to the geometric series as it's presented in the theorem is also true. So now instead of it just being an x, it was a 2x. And if we take that 2x and replace the x to the n portion and expand from there, we can see that it is exactly what the example is presenting, 2 to the n times x to the n. And then finally, by definition, this is true for x values less than 1. So in this case, if we're starting with a 2x, this would also be true for absolute value of x values less than 1/2. We're going to find a power series expansion with center c equals 0 for f of x equaling 1 over 2 plus x squared. And I'm sorry, I chopped off the rest of this question. And then it says, and find the interval of convergence. Okay. So we really have to make this fit the geometric, right? The 1 over 1 minus x. So we're going to manipulate it a little bit and say, well, 1 over 2 plus x squared. The first thing I would want to do is let's pull out a 1/2 so that I can find that 1. Right? That 1 in the beginning is important. So now I have 1 over 1 plus 1/2 x squared. And then finally, I needed to say 1 minus x in the denominator. So this is equivalent to 1/2 times 1 over 1 minus negative 1/2 x squared. Or 1/2 times 1 over 1 minus u, where u is negative 1/2 x squared. Okay? All good there? So if we use that equation from before, then we could say, so using equation 2, we could say 1 over 2 plus x squared is equal to 1/2, because we took that out, summation n equals 0 to infinity. Our u, or our x, whatever you want to call it, is negative 1/2 x squared to the n power. Okay. So I'm going to rewrite this a little bit, clean it up. Keep that half out there for a moment. The textbook puts it in there right away, I think, but it wasn't super clear to me, so I want to make sure you guys see it. So we have a negative 1 to the n, right? If I put that n into both terms up there, I have an x to the 2n over a 2 to the n. Right, so I'm just taking this n power and I'm putting it into my u, my negative 1/2 x squared. And then the next thing I'm going to do, or the last thing I'm going to do here, is I actually have a 1/2, which is like a common term over here. I can include this 1/2 in here and make this denominator 2 to the n plus 1. I'm increasing the exponent by just one more 2. So this expansion is valid if our u, absolute value of it, is less than 1. Or, if we manipulate this a little bit, the negative obviously doesn't matter because it's in the absolute value. Multiply by 2, square root it. We need to stay between root 2. So theorem 2, term-by-term differentiation and integration. We're going to do a couple examples here, and then there's another really long example related to differentials that I'm going to save for the textbook to show you, because it's like a 2-pager in the textbook. So it's saying, right, there's the power series up top, has a radiance of convergence, r is greater than 0. Then f of x is differentiable on c minus r and c plus r, so that interval. Or for all x if r ends up being infinity. So if you are convergent in your interval, then you are differentiable, is what they're saying here. Furthermore, we can integrate and differentiate term by term. So if we expanded a series and looked at individual terms, we could integrate and differentiate as we needed for any value inside that interval. Okay, so we're bringing in FTC part 1 here, where the big F prime versus the integral of big F, etc., having all of those, that notation back is something to look out for, what direction we're heading in. So the big F prime, the derivative of it, is said to be the summation from 1 to infinity of n times a sub n x minus c to the n minus 1. So it's like it's bringing back a previous term. Right? Think about how we use power rule and such. Right? If I'm deriving, I'm reducing, and I'm multiplying. Okay? So that's the derivative of power rule is showing up right there. And then the next one, if I integrated big F, right, I get an A, like that's my area, that's some constant. And then I have this summation where I'm adding 1 and dividing by the new. So they're just showing us in this notation that I can derive and do the summation, and I can anti-derive and do the summation. And I also have, when I do the anti-derive, I have that constant. That's where Like if you're looking at it, you're like, where's the n plus 1, where's the n? It's just power rule in either the derivative or the antiderivative direction. The series have the same radius of convergence. So essentially this is saying you are allowed to do this. And then when and how we do it, I'm going to show you in a couple of examples here. 2 examples. Okay, I'm going to change pages. Is that okay? So differentiating a power series. Prove that for values between -1 and 1, 1 over 1 minus x quantity squared is equal to 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the 4th, etc. Okay. So the first thing I'm going to look at is the fact that if we kind of removed that squared for a moment, then we can see that we have this geometric series, and r is 1 of this. If we just look at this portion of it, 1 over 1 minus x. And that would be equivalent to 1 plus an x squared plus an x cubed plus an x to the 4th, etc. Because that's our geometric series, and we had the x to the n, the summation of x to the n for that, for when it compared to the power series, okay? So I'm just going to make a note that that's by equation 2 previously in this section. So now, if we use this idea that we can derive, let's see where that takes us. If I derive the whole thing, if I derive the 1 over 1 minus x, and I derive each term over there, then I'm going to get, on the left-hand side, it is a quotient rule. You don't have to treat it as a quotient rule. You could change it to a negative exponent rule, etc. But it will derive and come out as 1 over 1 minus x squared. And the right-hand side derives and comes out as 0 plus 1 plus 2x plus 3x squared plus 4x cubed, etc. Which is exactly what we said. So we were able to use this idea of deriving to prove a power series is equivalent to that. And we based this one off of the fact that we did have kind of a geometric series in there to work with. This should have parentheses right there. Oops. Last example for today, power series for the arctangent. So prove this is true from -1 to 1. So it's starting as tan inverse of x is equal to this power series, this summation, 0 to infinity, -1 to the n, x to the 2n plus 1 over 2n plus 1. And we're proving that it's equal to x minus x cubed over 3 plus x to the 5th over 5, etc. Okay. So we're going to recall a couple of things right now. I'm going to recall the fact that the derivative of tan inverse is equal to 1 over 1 plus x squared. And I'm going to recall the geometric, just to have it, if we need it. 1 over 1 minus x is equal to the power series of x to the n. So if I, right, derive this tan inverse, if I derive what I started with, then I would have this 1 over 1 plus x squared, because that's tan inverse, equals summation from 0 to infinity and if I continue looking at that summation up here, right, I derived here, so if I were to derive here, thinking power rule, the 2n plus 1 would come down. I would subtract 1 from my exponent, and the 2n plus 1 from here, and here is going to end up canceling. And that's what I was missing on my notes. So using power rule derivative, then I end up having just a negative x squared to the n power. Everything else is gone. Or I can pull it out as a negative 1 to the n x to the 2n, to write that. Which would be equal to 1 minus x squared. I'm still just deriving, right? Now I'm on to the third part, because the 3 would drop down, the 3 would cancel, etc. Plus x to the 4th, minus x to the 6th, etc. So this line of work is just the derivative of this whole thing. Okay? I'm going to kind of chunk this off. So if we use theorem 2, and say, using integration now, tan inverse is equal to the integral of dx over 1 plus x squared, which would then be equal to the integral of 1 minus x squared plus x to the 4th minus x to the 6th, etc. What this allows us to do, it feels like we're going full circle a little bit, but our end goal is to figure out what that a is in that theorem. Okay, I'll be done in 30 seconds. So this is then equal to a, the integral of dx, etc., plus x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. So if x is 0, which falls inside of our domain, then a is equal to tan inverse of 0, and therefore a equals 0. So because we got this true statement, this is then equal to what we started with, and it's true for values between 1 and negative 1. So we definitely kind of went